one side of the proof. So what we want to do, we want to prove, the converse of this statement. Okay, so this side first. So I'm going to assume that K is closed and bounded, and I want to prove that K is compact. Okay, so for the compactness, I need to pick an open cover. So pick an open cover that cover K. But we know that K is bounded. So it has an upper bound and lower bound. So in other words, there is an open interval such that in which K is sitting. And I'm saying that now take V, which is everything in R except K. Okay? Then K and then the cover of K and V are going to cover everything in the real line. And hence in particular is going to cover A to B. Okay? Now, since A to B is compact, so there exists a finite subcover, which looks like this. And you have to be careful. It is possible that V is inside this cover, finite subcover. It's also possible that V is inside this subcover, but it's also possible that you don't need V to cover A to B. Okay? So you have two situations. If either you can cover A to B without V or with V, the argument would be same. In fact, you have in both cases a finite subcover, okay, for the interval A to B. But since A to B contains K, so the same cover also works for K. Okay, and hence compact. And K is compact. Okay, the CPT is sometimes used as a shortcut for compact. So what we should do next, this side. Let's do this. Okay. I'd like to prove now that if something is compact, it must be bounded, and it must be closed. Alright. So first I'm going to prove closeness. So I'm saying that suppose K is compact. Okay. I'm going to show first that K is closed. Okay. K is closed. What's the definition of being closed? So a set is closed if. So we have various characterizations. Closure is equal to K and so on and so forth. But the fundamental definition is that it contains its limit point. Okay? It contains its limit point. So I'll do it through contradiction. I'll say, imagine I have a limit point of K, but it's not part of Ki. And I'm going to show that it's going to lead you to a contradiction. So let X be a limit point of K, but X does not belong to. Okay. I'll show that I'm going to get a contradiction for the compactness of K. So in order to get a contradiction to the compactness, what we need to show? We need to show that there is a cover for which we don't have a finite subcover. Okay, this is what this is going to show. I'm saying define some sets UN, okay, and UN is what? Okay, UN is the interval of this one, where n is the natural number, minus infinity to x minus 1 over n, and union x plus 1 over n to plus infinity. Okay. Where n is what? So n can be anything. How does the UNs are going to look like? Let's try to draw a picture of it. Okay, x is somewhere here. So maybe k is compacted somewhere here. That's my k. Okay. And x is the limit point of k, but not inside k. So x is going to be maybe somewhere here, away from k actually. Okay. And I'm saying now take UNs. Okay. What would be for n equal to 1? What would be this interval? So this interval is going to be x minus 1 to minus infinity and x plus 1 to plus infinity. So while I'm making it approximate picture, so don't take it as so it's just a give to idea. So maybe x minus 1 is here and x plus 1 is here. So this shows that okay, this and this part is covered. Are you getting the point? What would be the second thing? X minus 1/2 and x plus 1/2. Okay, so it's going to be something like starting from here, maybe going to the same point. And where would be x plus 1/2? So it's going to be something like that. So starting from here and ending at plus infinity. So where would be x minus 1 over 3? Just think about it, what's going on. So we are getting gradually and gradually and gradually. So roughly I am saying that these numbers contains everything except x actually. Okay? They are going to contain everything except x actually. Okay? They can't contain x, for sure. They are going to contain everything except x. So here's the point. If these guys contains everything except x, are they not going to contain your k?
Yes.
Because k is away from x actually, it's outside, So it's going to contain your k as well. So what did you got? You got cover for k. Let's draw that up like that. Okay? So I'm saying then, and clearly if you take the union of I equal to 1 to infinity, that will be n equal to 1 to infinity of this UX, it's going to contain your k. Okay? It's going to contain your k. And I'm going to show that for this cover, you can't find a subcover, a finite subcover. Okay, for this cover. So it covers K, but you can't find finite subcover. Okay. Now, you take any n, in other words, this exist NA in case such that A is sitting inside this interval x minus 1 over n and x plus 1 over n. Why would such a A exist? Why would such a A exist? So how does x minus 1 and so how does what would be the U capital N actually? Okay. What would be U capital N? So it's going to be minus infinity to x minus 1 over n union x plus 1 over n x plus 1 over n to positive infinity. So this is what my and this set is what? Essentially this set is not exactly complement. It's not exactly complement, but if you add, for example, these two endpoints, then it's a complement of. So it's everything other than this set. It's not really everything because there are these 2 points which are missing. Because if you take the complement of this, you're going to get a closed interval x minus 1 over n to x plus 1 over n. Are you getting the point? Okay. And why this is the case, that there must be some A in here. So we haven't used, just think about it, we haven't used this thing. So what is a definition of the limit point? That every neighborhood contains the point of, that set actually. So if I'm saying that x is a limit point of k, then every small neighborhood of x, like x minus epsilon and x plus epsilon, contains an element of k other than x actually. This is what the definition. So I'm saying that, so since x is a limit point and this is a neighborhood of x, so there must be a point in k which is also here. Are you getting the point? Here is the thing. What would be the relationship between this set A, okay? This set A, not set but element A, okay? This implies that what would be the relationship between this element A and the union, which is from n equal to 1 to capital N UL. Keeping in view this information, what should be the relationship between this and this set? Mojda ho jayega. This would be a miracle if A belongs to here, because just think about it. Just think about it. A is here in this interval. Well, these are what? So you are taking everything other than, So does this set and this union can have anything in common with each other? They can't have anything in common with each other. So this is not going to be in this set. Are you getting the point? What does suppose that in K I found an element which is not in the any of the finite subcover, because this n is any arbitrary line. So it's not in the any of the finite subcover. So I have found A which is not in, what do you call this finite subcover? What does it mean? It means that there are points in K which are not covered by the finite subcollections of this open set. And hence K is not compact. But K is compact actually. So it's a contradiction. Okay? It's a contradiction. This implies this un n belongs to n has no finite subcover, and that's a contradiction. That's a contradiction. Okay. You can see that. This thing is wrong. If this thing is wrong, what is true? That x belongs to K. Take a limit point, it must be in K. And hence K is closed. Alright. Next thing that I would like to prove that. Now I have closeness and compactness of the set K. What I would like to prove is that it must be bounded as well. It must be bounded as well. Okay. K is bounded. What is the meaning of being bounded actually? Is upper bound and lower bound. I'm saying suppose not. Suppose K is unbounded. Okay? What does this mean actually? Suppose K is not bounded. Consider this cover for K. Keep in view that we have the compactness of K. So consider this set now, un such that minus n. Okay? un minus n. Then, what do you think? What's the relationship between U1, U2, in other words, this collection and K? So how does UN look like? So what is UN? There's minus 1 to 1, and minus 2 to 2, and minus 3 to 3, and so on and so forth. What do you think? So their union is going to cover whole R actually. Think about it. So if you add this into this, so it's cover whole R. So if it's covering whole R, it must cover. Okay. this is a cover form. I'm going to show this cover has no finite subcover. Okay? I'm going to show that this cover has no finite subcover. Take some n from n. So see, so far I haven't used the unboundedness of K actually. What do we mean by unbounded actually? Just think about it. Forget about all that. Just think about it. So bounded means something which has upper bound and lower bound. Unbounded means something it doesn't have upper bound and lower bound. What does it mean? Okay. So if I want to be precise.
कोई भी नंबर सर अगर हम उठाएंगे तो उससे बड़ा भी एग्जिस्ट करेगा.
Exactly. So if you take any number, you can always find an element which is bigger than that number or smaller than that number actually. Okay. So take n and n. Okay. So since K is unbounded, K is unbounded. So there exists an A in K such that its absolute is bigger than n. Absolute is bigger than n. Agree? Absolute is bigger than n. What does this mean? This absolute of A bigger than n represents what? If I want to see it explicitly, it's an interval. Okay? It's an interval. So if n is here, minus n is somewhere here, then when I'm saying that absolute of A is bigger than 1, so it includes this part, excluding this part, includes this part, excluding this part. Okay? Alright? Or it's in this set. A is in this set. So either here or. Okay. So here's a question. What would be the relationship between A and the union of UNs from n equal to 1 to capital N? Doesn't belong. Okay? Why? Because this is what? So it's minus 1 to 1, minus 2 to 2, minus 3 to 3, up to union minus n to capital N. You know, eventually this would be equal to U capital N, essentially. Yes, it doesn't belong to this basically. Okay. And what does this shows actually? So again the same situation. That if you take finite such, open sets, they don't contain a point A actually. So in other words, any finite cover, any finite subcover, or any finite subcollection of this collection is going to contain a point, okay, for each such finite collection of open intervals, there would be a point in K which is not in this basically finite subcollection. So whenever you take a finite subcollection, okay, there would be a point in K which is missing. So that means that finite collections cannot cover the whole of K. And hence what does it shows? That U1, U2, U3 has no finite subcover prediction. Prediction to fact that K is compact. Okay? K is compact. And we are done with this Heine Borel theorem. ठीक है. So, what we just showed, we showed that, definition of compactness, at least in R, is equivalent of being closed and bounded at. So it's not necessary that you want to prove something to be compact. Okay, you just show that every finite cover, every cover has a finite subcover. There's no need to do it. Now just check that whether it's closed, does it contains all of its limit point, and is it bounded? Okay, then your life is easier. Are you getting the point? But the thing that played a crucial role in proving this was this, that closed interval A to B is compact. Okay? We can extend this result in Rn. Okay? And we can show that this result is also true in Rn actually. So for a Euclidean space, okay, with respect to the Euclidean topology, okay, the usual metric on Rn, we can prove that every set that is closed and bounded, okay, is compacted. Okay, this has lots of consequences, especially it has lots of consequences in geometry actually. In geometry, we are interested in compact objects actually. Okay, so it's like a compact surfaces, compact manifolds actually. Okay, so this has what you call a deep consequences in geometry as well. Okay, but this is not. So Heine Borel theorem is not true in general in all topological spaces. This is not the case actually. But okay, it's not true that you take any topology and you take any compact set and it must be closed and bounded. Okay, so it's only restricted to some special kind of metric spaces. Okay, some metric spaces in which this result is true. Okay, are you getting the point? So this is Heine Borel theorem. So let's have some fun with.
सर हमने जो लेमा किया कि सर क्लोज सेट जो है वो हमेशा कॉम्पैक्ट होगा, उसके लिए सर इतना हमने प्रूव किया। उसके लिए हम कोई भी सर इंटरवल लेते थे, ए और बी इंटरवल था क्लोज, तो उसके लिए हम कहते हैं किसी भी एप्सिलॉन ग्रेटर देन 0 के लिए ए माइनस एप्सिलॉन और बी प्लस एप्सिलॉन कर दें। तो ये एक सर फाइनाइट कलेक्शन भी हो गई, एक ही सेट है,
फाइनाइट कलेक्शन
ओपन भी है और उसको कंटेन
finite, okay, it's not that simple. Finite sub collection of which cover? Give me a cover first, and then